And then last, before I answer questions, I thought I would give you a little demonstration of measuring noise canceling headphones. This is becoming very, very common now in headphones. Basically what is done is the headphones have some microphones built in, and basically you have kind of a feedback loop. So the idea is that if you input some noise, or take a very simple case, put a sine wave on the outside. So what's going on here? So we want to keep the noise from entering into the ear. And we can have both what we call passive attenuation, which is just if we block the sound from getting into the ear, as well as active cancellation. And with active cancellation, we actually will pick up the signal on the outside of the headphone and then phase invert it to try to cancel out anything that gets inside the headphone, which will, in theory, if anything's 180 degrees out of phase, it will cancel completely. So what I'm going to do here is I'm going to play pink noise through this loudspeaker to simulate background noise. And I'm going to measure the headphones for both passive as well as active cancellation. And let me just show you the next slide here. So there's going to be 3 measurements. The first one is called unoccluded. And basically, this is without the headphones on. And we want to establish, I'll call it a baseline. We want to decide what level we want to test at. I'm going to test at 90 dB SPL. And if I was really careful, I wouldn't just use one loudspeaker. I'd use a bunch of loudspeakers to simulate sound coming from every direction. But for this demonstration, it's a lot easier to just use one loudspeaker. And then passive attenuation is, again, with the headphone on, but without the noise cancellation circuit, or the cancellation circuit off. Then I turn the active cancellation circuit on and measure again. And the important thing here is what I'm looking for is attenuation. I want to know how much noise gets reduced. So we're going to look at relative measurements relative to what we call unoccluded. So passive isolation will be the passive attenuation compared to the unoccluded ear. And then the active will be the active cancellation switched on. And it also includes passive attenuation now because both are working together. And that will give me the total active component, or the total noise cancellation. So let's do that. Let's switch to sound check. Okay, so here's my setup. Let me just get rid of this for a second. So I have in SoundCheck these sequences, and I've created one called Noise Cancellation. And you can see it's pretty straightforward. It's going to play some pink noise at a particular level. So here's my pink noise, and I can set the level over here. Maybe we'll go for 90 dB, I think is a little better. Now it is possible that especially the active noise cancellation circuit will change its effectiveness with level, because quite frankly, at higher levels, it needs more amplification to cancel. So it is a good idea to try doing it at different test levels. And for today, I'm just going to measure from 10 kilohertz to 100 hertz. It depends on the loudspeaker, how low in frequency it can go, because I'm equalizing it. I want to measure at a constant sound pressure level, so if I have a little loudspeaker up here and I try to tell it to output 90 dB at 20 hertz, I'll probably blow up the loudspeaker. So we don't want to do that. And part of this test requires what we call the real-time analyzer. And the real-time analyzer is actually going to be done in, I believe we're doing in 12th octaves. And if we look at the frequency, sorry, 3rd octaves, you can do it in whatever resolution you want, but typically when you see specifications, they'll do it in so many nth octaves. I guess if it were me, I'd probably do 12th octave, but this is typical of the standards is 3rd octave. And in this particular case, 100 to 10 kilohertz is the range we're going to look at. So let's start it. So I have a little message step. A sound check can do a real measurement, or it can recall stored, saved measurements. So I'm just going to say, no, let's measure this. So 5 seconds of pink noise. And notice it should be flat because I equalized it. And now what I'm seeing is my spectrum of the pink noise measured in the ear simulator. So that's kind of my reference. So now I want to measure the passive attenuation. So no cables, just headphones. I got the active noise cancellation circuit off, and I probably should get the channels correct. So here's, and again, the seal is going to make a big difference to how well it attenuates. If I put some earbuds in there, forget it. I'm going to get no attenuation. If I have in the ear like this, that seals the ear canal, it's still going to give me some good attenuation. So now I just say enter. Now this is very interesting. So here we have the green curve, which is just the passive attenuation. And if you notice, if you look kind of carefully, you'll notice it's kind of strange. Why is the green curve slightly above the unoccluded ear? And you would say, well, that's impossible. I put the headphones on. How do I get a gain at low frequencies? Well, what happens is when you, just think of this. If you put your ear, and you cup it, your hand, and you cup it over your ear, you're actually creating kind of a resonance, which is going to cause an amplification at low frequencies. So just by the mere fact that the headphone is sealing my ear means that I'm getting a resonance due to that cavity now. So that's causing a little bit of gain here, but it's a dB or two, nothing significant. So now I'm going to turn the active noise cancellation circuit on, and my green light should come on here. Good. And then I'm going to hit enter. And now we see the total. So this is kind of neat. We got the yellow curve here is now both active and passive, right? Because we still have the passive attenuation, but now we have the noise canceling circuit turned on. And again, something interesting happens. We get a little bump here. So at low frequencies, this is great. We're getting on the order of 20 dB of attenuation. But if you look carefully, the difference here is the active noise canceling circuit is, instead of attenuating, it's actually amplifying, which is not what you want. But the noise cancellation circuits is a feedback loop. And that feedback loop has basically a high frequency limitation. It I don't think it doesn't matter how well you design your noise canceling circuit, you're going to see some of this. And what's happening is, at the higher frequencies, instead of it being a feedback where it's canceling, it's actually feeding back on itself and causing a gain. So it's no longer 180 degrees out of phase, it's actually somewhat in phase. So we typically see this little bump, and it's just a compromise. So if you look at the two together, you say, okay, this is my total. I got almost no difference at the high frequencies by turning the active gain circuit on. But if I combine the two, I'm actually getting this red curve here, which is my total attenuation. And I can get 20 dB at low frequencies, 15 dB at 2 kilohertz, and then at very high frequencies, about, 5 kilohertz and up, I'm starting to get as much as 30 to 40 dB attenuation. Yeah, it's a good idea to do this in a quiet room. Yep, now you can see it's a little different.
Because of background noise.
Well, also the seal. I think the slightly different seals. Yeah. So really the more important one here. So here we have two different sets of measurements. The green and the red are the last two. And you can see they're pretty similar, but there is some difference depending on the seal. You can see I think I got a better seal the first time than the second time. But that, again, that's why it's important to do the averaging or the repositioning, because if I really wanted to get a good seal, I'd probably push really hard and make sure it's nice and snug, which is the reality of these kind of measurements. Okay, so that's it for now, and I guess we said 12:30 to 1 we had time for questions, or?